Today we're going to prove that an AVL tree with n nodes has height big O of log n. Now, if you're not sure what an AVL tree is, it's just a binary search tree that's height balanced. So if we look at this example here, our tree on the left-hand side is an AVL tree. That's because it's a binary search tree first, right? Every left child has a value smaller than its parent, and every right child has a value larger than its parent. And also, every node's left subtree and right subtree have a height that differs by at most 1. But you'll notice that on the right-hand side, it's not an AVL tree. While it is a BST, right, 2 is less than 5 and 5 is less than 10, our root node 10 has a left subtree of height 2 and no right subtree. So all we're going to do is give a lower bound for the number of nodes required to make a tree with height h, right? So we're going to give a minimum number. To do that, I'm going to create this function big N of h, and I'm going to say that that's the smallest n needed to make my AVL tree with height h. Now, before we jump right into this here, you should start thinking about the base cases of our function big N of h, right? You'll notice that n of 0 is 0, n of 1 is 1, n of 2 is 2, and n of 3 is 4. And you might start to see kind of a pattern there, maybe some Fibonacci-esque series stuff. But in either case, you should really draw out these base cases and see what you can do, see what's not an AVL tree, and go from there. But if we create a general formula for n of h, we're going to see that it takes on the value 0 when h is 0, 1 when h is 1, and then it takes on the value n of h minus 1 plus n of h minus 2 plus 1 for h greater than or equal to 2. And the key insight here is that an AVL tree of height h with the smallest number of nodes must have a subtree that is an AVL tree of height h minus 1 and another subtree that is an AVL tree of height h minus 2. And both of these subtrees must have the minimum size. Now that's true because if we had two subtrees of a larger h, right, our subtree would no longer be the smallest tree of height h, right, if both of them were h minus 1. And similarly, if they weren't individually the minimum size required to get that h, then again, our tree would no longer be the smallest tree of height h. So now that we have this recurrence, we can solve it. And this is a bit easier than it looks, so I do suggest giving this a try yourself. But if you have no experience with this, you can just take a look at how I do this. So first, I'm just going to assume, without loss of generality, that n of h minus 1 is greater than n of h minus 2, right? We're just picking one of the subtrees and we're saying that one's larger. And then from there, I'm just going to, plug that assumption into my current recurrence. And then I'm going to n of h minus 2 plus n of h minus 2 plus 1 is less than 2 n of h minus 2. And that's just because I'm dropping the plus 1, right? Now our next step is really the recurrence magic. I'm just going to be tracing the flow of this recurrence, each time subtracting 2 from h and each time multiplying by 2. And then eventually you'll see that n of h has a lower bound of 2 to the power of h divided by 2. And then we can do a bit of trickery here, a bit of voodoo. All we have to do is take the log of both sides, and then, our 2's cancel out. And then I get h of 2 is less than log of n of h, right? And now we're almost done here, because immediately, due to the properties of asymptotics, right, we see that h is O log n. Since my n, my smallest n required to get a tree of height h, is that function big N of h. And then we're done.